How did computers finally learn to see? And it's a huge question. I mean, it is absolutely central to almost everything we think of as modern AI. Right. Like a self-driving car that needs to know instantly if that's a pedestrian or a trash can. Exactly. Or automatic character recognition, reading millions of documents. It all comes down to image classification. But here's the core problem, the big disconnect we have to start with. To a computer, an image. It's not a cat. It's just a giant organized grid of numbers. Pixels. Just numbers. Brightness, color intensity. That's it. So how do you get from that, from this sheer numerical data, to the actual concept of a cat? We are tackling convolutional neural networks, CNNs. This is the one architecture, the single breakthrough that really solved how to capture visual structure. So today we're going to walk through why the earlier attempts failed, introduce this revolutionary idea of learned filters, and then break down the components that make CNNs so efficient. And then we'll get into the advanced stuff, how we make them robust, using things like transfer learning to bring them out of the lab and, into the real world. Okay, so let's start where AI so often starts, with a failure. The first attempts used standard neural nets, right? The multi-layer perceptrons, or MLPs. What was the approach there? The approach was, well, brutally simple. They'd take an image, a 2D grid if it's grayscale, a 3D block for color, and they would just flatten it. Flatten it. So just line up all the pixels end to end. Exactly. One enormous single input vector. Just a long line of numbers fed straight into the network. And you immediately hit two massive problems. First, just the scale of it. Oh, the scale is astronomical. For even a medium-sized image, that vector becomes so large that training is almost impossible. And the second problem is maybe more philosophical, but it's just as bad. When you flatten an image, you destroy the most important information. You destroy the structure. The relational structure. A pixel only means something because of the pixels next to it. If you treat the top left corner and the bottom right corner as just two numbers in a long list, you lose the lines, the curves, everything. Not only that, the whole system becomes incredibly brittle. We can recognize a chair if it's rotated a few degrees or shifted over it. Yeah, sure. To that flattened network, a rotated chair is a completely new, massive set of input data. It has to learn it all over again from scratch. It just can't handle translation or rotation or scaling. This challenge actually led to some really fascinating work before deep learning, trying to manually engineer ways to find structure, like edge detection. Right, before CNNs, we basically had to tell the computer what to look for. Hey, find a dark line next to a bright line. We were doing the thinking for it. That's where you get things like the Sobel filter. Precisely. The Sobel filter uses these small matrices, these little grids of numbers, and you slide them over the image, pixel by pixel. And for you, the listener, this operation is fascinating. You're basically matching this little filter over a patch of the image and multiplying the numbers. That's it. If the pixels under the filter are all the same, the result is 0. But if there's a sharp change of gradient, an edge, you get a big number. We spent decades handcrafting these filters. And that central idea, applying a small filter across a big image to find local features, that's the key insight that CNNs automated. But okay, let's get to the solution. You said CNNs use structured data. Correct. The input isn't a vector, it's a tensor. Okay, that sounds a little jargony. Let's break that down. If a matrix is like a flat spreadsheet, x and y coordinates for pixels, what's a tensor? A tensor is basically just a stack of those spreadsheets. It's got 3 dimensions, x and y for the image width and height, and then a third dimension z for depth, the channels. So for a grayscale image, the depth is just one. But for a standard color image, like RGB, your tensor is 3 layers deep, and the CNN keeps that structure for its first few layers. Which brings us to the really revolutionary part, the convolutional layer. This is where the CNN just completely breaks from that old MLP model. It does, and it's loosely inspired by neuroscience. By the way, our brains process vision in these hierarchical layers. The key idea is sparse connections. Sparse connections, meaning a neuron in a convolutional layer doesn't get input from every neuron in the layer before it. No, not at all. It only gets input from a tiny localized subgrid of the previous layer, just a small little window. So we only look at a small patch of the image at a time. What are the key parameters that control that window? There are 3 main ones. First is the kernel size, or filter size. That's the dimensions of the window itself. It's usually really small, maybe 3 by 3 or 5 by 5. Small enough to just capture, say, an edge or a corner. Exactly. The second parameter is the stride. That's the step size. It's how many pixels you skip when you slide that kernel to the next position. Usually just 1 or 2. Yep. A stride of 1 is very common because it lets the windows overlap so you get this nice continuous coverage. And the third one is padding. This is where you add extra zero value pixels around the edge of the image. Why do that? It's mostly a mechanical trick. With a stride of 1, padding makes sure the output size of the layer is exactly the same as the input size. It just keeps things tidy. Okay, so we have the window, the step size, the padding, but the absolute game changer, the thing that makes CNNs actually work at scale, is parameter sharing. This is the core insight. It's the difference between mass redundancy and real elegance. In a normal MLP, every single connection has its own unique weight to learn. Right, and we said for a simple 64 by 64 image, that could be 16 million different weights to train, which is just impossible. It's totally intractable. But in a CNN, the weights for one filter, that 3 by 3 kernel, are identical. They're shared across every single neuron in that layer. Whoa, okay, so instead of trying to teach 16 million different neurons how to spot a vertical line, you teach one master filter what a vertical line looks like, and then you just apply that one filter across the entire image. So that one shared set of weights is the filter. The network learns the filter automatically. It learns what curves, edges, colors, and textures look like on its own. Precisely, and the scaling is where it just becomes mind-boggling. That old MLP layer needed 16 million weights, a convolutional layer with a 3 by 3 kernel. It only needs to learn the filter. That's 9 weights plus 1 bias, 10 weights total. From 16 million down to 10. It's an incredible reduction. And of course, you don't use just one filter. You might learn 32 or 64 different filters in a layer. But even with 32 filters, you're only learning 320 weights. That efficiency is why we have modern computer vision. That's a beautiful solution. Okay, so after one or more of these filtering layers, the network usually has a pooling layer. Why do we need to manipulate the data again? Pooling has two jobs, really. It compresses the data, reducing the resolution of the filtered image, and it also helps the network start to relate features that are a little farther apart. Does this pooling layer have weights to train too? No, and that's a key point. Pooling is a fixed computation. There are no parameters to learn. It just takes a small, non-overlapping grid, say, a 2 by 2 block, and replaces it with a single value. And that's usually just the max value from that block. Almost always, it's called max pooling. You just take the biggest number from the 4 inputs. It's simple and it works. Okay, so we've filtered the image for features, we've compressed it with pooling, but before the final classification, there's one more step. We have to flatten it. We have to undo the structure we worked so hard to keep. That's right. It seems counterintuitive, but after all the convolutional and pooling stages, the final tensor grid is turned back into one long vector. Why? We lose that relational structure, yes, but only because the very end of the network needs that traditional flat input vector. And that final section is made of one or more fully connected layers. So the network basically turns back into a standard MLP right at the end. It does. And even after all the pooling and parameter sharing, this final section can still have a lot of weights to learn. But now, it's learning to classify high-level features, not raw pixels. And it's trained like any other network, with backpropagation. The labels, dog, cat, are encoded using one-hot encoding. Yep, and the very last layer uses a softmax activation function, which gives you a nice, clean probability distribution. The network can say, I'm 85% sure this is a dog. So now we have the architecture. But making a CNN that's actually useful in the real world is about more than just the design. We need to make it robust. Let's talk about data augmentation. Data augmentation is huge. The goal is twofold. First, you improve accuracy, especially if your data set isn't that big. And second, you teach the network to be insensitive to small real-world changes. So we're creating new artificial data by messing with the images we already have. Exactly. You generate new training examples by taking an image and maybe shifting it a few pixels or rotating it slightly or even flipping it horizontally if that makes sense for your problem. And that teaches the network that these little changes don't change what the object is. Right. And it's all automated now. Tools like the Keras image data generator will just randomly apply these transformations to the images as they're fed into the network for training. It's a constant stream of new variations. That's a great technique. But what if training a big CNN from scratch is just too expensive? That brings us to transfer learning. And transfer learning is maybe one of the most powerful ideas in all of modern AI. It's just reusing knowledge from one big problem to solve a new related problem. And CNNs are just perfect for this because of their layered structure. Those early convolutional layers learn all the universal stuff. Edges, corners, textures, general shapes, the building blocks of vision. Those filters are useful for pretty much any visual task. Whereas the final, fully connected layers are where the very specific knowledge is. Telling the difference between 1,000 breeds of dog. That's it. And a great example from our sources is the VGG16 architecture. It's massive. It was trained on the huge ImageNet database. The scale of VGG16 is just wild. It has 138 million parameters. Training it took, 2 or 3 weeks on 4 powerful GPUs? It's the definition of computationally expensive. So if I, the listener, want to use VGG16's amazing visual knowledge to classify, say, different types of rare insects, I don't have to start over. You absolutely do not. You use transfer learning. You take the pre-trained VGG16, you freeze the weights on all those powerful general-purpose convolutional layers. You lock them in place. You lock them in, and you just chop off and replace the final specific classification layers with fresh ones. Then you only have to train those new layers on your insect pictures. So you're basically borrowing the model's eyes. That's a perfect way to put it. You borrow its ability to see, and you just retrain the part of its brain that makes the final decision. It's the ultimate shortcut. You're saying, I already know what features look like, just teach me how to combine them to identify this specific beetle. So when you step back, you see we've gone from treating an image as this chaotic list of numbers to filtering it with shared learned weights, compressing it with pooling, and finally classifying the distilled features. It's an incredible architectural journey, but the final thought we're left with is just how much choice is still involved in designing these things. It's a huge design space. Yeah, and building a really good CNN is still as much of an art as it is a science. You have to tune so many things. The number of layers, when you apply pooling, your activation functions. Kernel sizes, how many filters to use? Is it 32 or the thousands? Do you use padding? What's your stride? Which kind of pooling do you use? And the success of the whole network comes down to finding that perfect combination of choices. The perfect combination, so that the set of filters your network learns can accurately and efficiently capture the visual essence of whatever you're asking it to see. And that ongoing search for the perfect, the most minimal, the fastest architecture, that's why CNN design is still one of the hottest areas of machine learning research today. It's a never-ending quest to teach machines to see our world a little bit better and a little bit faster than we can ourselves.